Hey everybody, welcome back to another round of engineering. And yeah, let's get at op amps. So I had some example problems ready for you, and we'll just hammer through a couple of them just to get a feel for the various op amp circuits. So what we have before us is this sucker. Oop. So what we have before us is this sucker, and I've taken the time just to write it out. So what we want to do, we want to calculate the output potential when the source potential is 3.6, and excuse me, I've dropped my units here. I go 3.6 volts. There we go. And specify the range of the source potential to avoid amplifier saturation. Okay. So we have two things. Go ahead. You got it? Good, good, good. And let's not forget our two golden rules. Those will always help us here. So number one is that the negative input will equal the inverting input will equal the non-inverting input in terms of potentials. And number two, I into the op amp is 0. Okay. So let's remember those two. And I'll go ahead. Let's go ahead and call this node A. I'll call that one node B right there. And then we are off and rolling like a bale of turtles. So right away, we can apply our first golden rule to state that the potential at A must be 0. And again, that's based on the idea that our golden rule tells us these two have to be at the same potential, and we notice that that is grounded. So right away, we've got a value for the potential at A. Let's go ahead now. We have two more things to write down. We need to write down the node voltage equations for both A and B. Let's go ahead. So for A, okay, so we have the left branch, and we're assuming that current is flowing out from A. So we have VA minus VB over 80K. And that whole rigmarole equals 0. Again, I'm using the second rule here. The other golden rule telling me the input current to the inverting input is 0. Okay, so let's check B now. We've got VB minus VA over 80K. Excuse me. 80K. Plus, and here we remember that the output can still provide some sort of current, so we better put an I in there. And that whole rigmarole equals 0 again. Sweet! Well, now we're good to go. There's a 0 there. Okay. So let's sub and solve. Okay. So what do I get? Well, I'll go ahead and use this middle equation to find VB. So I get negative VS over 16K plus negative VB over 80K equals 0. Okay. Finding VB, we get something like VB equals VS, get a negative sign, and let's see, 80 over 16, 5. All right. So we notice that this will amplify the signal by a factor of 5. Okay. Sweet. Okay, well, I guess the problem doesn't actually specify for the current. We could find it if we wanted to. So let's go ahead. We have the current will be equal to negative VB over 80, okay, which will equal, well, 5 divided by 80 is 1/16. And so we get something like negative Vs over 16. Okay. Just like we expected. Okay. Well, of course, the problem is asking us up here. Okay. And it says that Vs is 3.6. So 5 times 3.6, well, 5 times 3 is 15, plus another 3. So this would be 18. So VB would equal negative 18 volts. And we're done. Well, for the first part. There we go. Let's circle that in yellow. We now have what the potential, the output potential is when the input potential is 3.6. Okay. Good so far? The second thing I was thinking about was this amplifier saturation. So let's go ahead and go through and get a feel for how do we figure out the amplifier saturation. Okay. So remember, I said, hey, V out must always be less than, and I put a magnitude sign in here, but I'll say the power, the op amp power. Okay. And maybe I should say the high, I'll say op amp power high, and it must be greater than V op low. And by that I mean this side, for the problem that we have, you notice that we have a negative number. Okay. We have a negative 15. So here, the output must be between negative 15 and 10. Well, we're fortunate enough, we actually have an expression for V out in terms of the source. So we're going to take this idea and we're going to plug it in right there. Okay. We have the gain and we have the source potential. So now we're just going to make that substitution right in here. And so we get something that says negative 15. We have V out, which we'll express as 5 Vs, and 10. Now, of course, we have to divide through by 5, negative 5. And when we do the negative sign, we have to flip the directions. So we end up with 3 less than V source, which has to be greater than negative 2. And so right away, we see that we must have hit the saturation limit. So if we were actually to give it an input voltage of 3.6, rather than measuring 18 as the output voltage, we're actually going to get V out is equal to negative 15. Okay. C'est la vie. Can't do it. Cool, huh? Okay, on to the next problem. So I've got another problem queued up here for you. Circuit on the left-hand side, and we're going to answer 2 questions. The first one, calculate the power delivered to the load, so this 16 kilo ohm resistor. And then the second piece, which we'll discuss on the next slide, repeat the power calculation with the op amp removed and the source connected directly to the load. In other words, we'll have our source, the 48 kilo ohm resistor, and then the 16 kilo ohm resistor, and then to ground. So go ahead, take a crack at the first part. Got it? Good, good. Okay, well, I'm going to go ahead and apply node voltage. And in particular, let's see if we can get an idea about what the potential is right here. So I'll call that node A. I'll call this one node B. And let's see if we can hammer through the circuit. So if I consider node A for a moment, node A, Okay? We are going to take advantage of our golden rule. Our golden rule states that the input current, so I in, must be equal to 0. Okay? And so what does that mean? That means that the drop across my 48 ohm resistor has to be, yeah, you see it? 0, right? The drop across the 48 ohm resistor is equal to the current flowing through that circuit times the resistor value. Put 48 here. But if the current in that branch is 0, that means that the drop, or excuse me, the potential drop across the 48 ohm resistor must be 0. There's no current flowing. So here's the next question. What can you tell me about the potential at A? Yeah, it seems goofy, right? Because there's no current flowing, there's no drop across the resistor, and therefore the potential at A must be that 320 millivolts. So we're not even using node voltage here. We're just going straight with the golden rules. So I'll put in, it's always good to remind yourself that you're using a golden rule. So we'll put GR there. So let's go ahead now and take a stab at node B as in boy. And keep it in mind your golden rules for operational amplifiers. What's VB going to be equal to? Yeah, you got it? Yeah. Remember, one of our golden rules tells us that the potential of the inverting input should equal the potential of the non-inverting input. And since there is no resistor in the feedback branch, we can say that our potential at node B equals the potential at node A, which of course is 320 millivolts. So lastly, what's the current in the feedback loop approximately? Yeah, 0. Good. So you can kind of think of all of the current that exits the op amp flows through our load resistor to go to ground. Okay. So lastly, let's answer the question now. We've got all of the information that we need to answer our question. We're asked what's the power delivered to the load. So I'll subscript that as 16. Okay. So we have V squared over R. So we have something like 0.32 squared over our 16. Put K here. Okay. I get something like 66.4, and I'll go into microwatts. Micro being 10 to the negative 6th. Okay. So I get 6.4 microwatts. Not very much. Right. Good so far? Okay, good. So we are done with the first part of the problem. Let's go ahead and look at the second part for a moment. The other situation where I connect directly my voltage supply to my 48 kilo ohm resistor, to my 16 kilo ohm resistor, and then connect it back to ground. So what is the power delivered to the 16 kilo ohm resistor for this situation? Hopefully you got it. You see where we're going to go. Well, here we have two resistors in series. And so what we can do is we can find the current. That's simply given by the potential divided by the two resistors, the sum of the two resistors. Okay. And so if we want the power for the 16 ohm resistor, we need the current squared times the resistance. And taking our substitution and plugging it in, what we end up with is, I'll go ahead and do it in variable form first. We have V over R48 plus R16 squared times R16. And plugging in our values, we have 0.32 divided by 0.32 squared. Don't forget the squared. Then we have a 64K squared. And then we have a 16K. And here I end up with something 0.4 microwatts as the power delivered to the 16 ohm resistor. And you shouldn't be surprised that it's different, because what happens is that since current flows through both of these resistors, you're going to get a potential drop across the 48 ohm resistor and across the 16. Right? So in other words, this 320 millivolt potential, let's see, 3/4 of it is across the 48 ohm resistor, kilo ohm resistor. So this is 3/4 of the drop. And then only 25% occurs across the 16 kilo ohm resistor. So how does the op-amp circuit avoid that? Remember that when we put the op-amp circuit in, it doesn't allow current to flow in that 48 kilo ohm resistor, which means we get the full drop across the 16 kilo ohm resistor. It's cool, right? Just to let you know, this form of a circuit where you do not have a resistor between the output and the inverting input, okay? This is called a follower circuit. In other words, the output of the op-amp follows whatever the input is. And you can see the advantage of this is that it isolates, for lack of a better word, it isolates your load from whatever resistor you have preceding the op-amp. It makes sure that all of the power is delivered to the load rather than being split between the resistor and the load. So imagine this. You know, for example, one last note, you can hopefully see some of the advantage to this. So if you had a Thevenin circuit, you know, based on passive elements, that the best you can do, the maximum power transfer that you can do to your load is 50%. Right? When the load resistance equals the Thevenin resistance, the power delivered to the load is only 1/2 of the total. Right? That's the maximum that could possibly be transferred to the load. Here now we have a way to transfer, to make sure that the full power gets to the load. Right? You could imagine for a moment that now what we could do is take our Thevenin potential, run it into the non-inverting side of the op-amp with a follower circuit. Excuse me, I forgot the Thevenin resistance. So we do this, RTH. We run it to now our load. And then to ground. And now we can make sure that our load actually gets, I'll say, power total. You say, by what magic does this happen? Well, don't forget again, there is an external power supply here, right? Good. Cool, huh? I think it's cool. Okay, good. Let's go ahead. Let's do another problem. Okay. So, I'll let you ponder this circuit for a second. Find the output voltage when the variable resistor, that's represented by Rx here. So if you don't like variable resistor, you can substitute in the word potentiometer. Potentiometer. Or I think people sometimes just refer to it as a pot. Okay. So find the output voltage, V out, when the variable resistor, Rx, is 60 kiloohms. Okay, that's number one. Number two, how large can Rx be before you saturate the circuit? So we'll cover both of those in turn. Go ahead, take a minute, hammer it out. You got it? Yeah, good. Okay, let's go at it. Now you can see right away that it's not a follower circuit. There is a resistor placed in the feedback loop. Okay. So that's one thing that we should take note of right away, is that it's not a follower circuit. And yeah, let's go at it. Of course, it looks a little different now, right? We have things connected to the non-inverting input. So one of the reasons I gave you this problem is I want to give you an example of other types of ways you can use the op amp. And we'll start applying our golden rules and falling into some of these really cool circuits just naturally. So let's go ahead. I've got 3 nodes now. So I've got node A right here. I'll call this one node B as in boy, and I'll call this output node C. Okay, so let's go ahead and run it. Now, I'm going to run it in terms of variables here just so that we can get an idea about what this op amp circuit is actually going to do. Okay, so I'm going to run in terms of variables, then later on we can actually solve it with the numbers. Okay, well, node A, we'll go ahead and write down. We have VA over, I'll just call this R45 for a moment, 45. Okay. And then we have plus VA minus VC over R63. And again, I'll use my golden rule and say that there is no input current into the inputs, and so I can set that whole rigmarole equal to 0. Well, let's consider node B now, and we see that it's not grounded, but it's at some non-zero potential, and so we'll go ahead and write out this one. We have the left part, VB minus, I'll just call this V for right now, V. Actually, to be more specific, I'll call it V400. And that whole rigmarole is divided by 15, R15. And then added to that would be the potential of B divided by Rx, our variable resistor. And again, using the golden rule, I'll say that there's no current flowing into the input, so I can set that all equal to 0. C. Well, again, I have VC minus VA, all divided by R63. And then added to that is the current running into the output of the op amp. And I will set that all equal to 0. And lastly, we'll use our other golden rule to state that VA must be equal to VB. Now, like I said, I'm going to go ahead and solve these in terms of variables, just so that we can get an idea about what this op amp will be doing. So in particular, you notice the second equation that I've written we can actually solve that for VB straight away. Okay? So let's do that. I have something like the VB times 1 over R15 plus 1 over Rx, right, equals my potential source divided by R15. Okay. Well, that's spiffy. Let's go ahead. So I get something that says VB, and if I move this to the other side, I get something that says VB equals V400. And then I'm going to write this as a fraction. Let's see, I get something that says Rx times R15 divided by R15 times R15 plus Rx. So what I've done is just found the common denominator. That's the Rx, R15, and then when I flip it, moving it to the other side, I end up with it in the numerator. Of course, we see that this term in parentheses is unitless, and oh goody goody, I can even cancel something out, so I don't have to worry about that right here and right there. Cool! Well, now I've got an expression for VB, and using my fourth equation, this is also equal to VA. So let's see here. Well, now that I have an expression for VA, I can use my first equation to find VC. So let's go ahead and do that. So I have something that says VC over R63 equals VA times 1 over R45 plus 1 over R63. Oh, that's going to look ugly, isn't it? Such is life. So here we go. Let's get it. We'll substitute in our expression for VA. So we have the potential at node C is equal to V400 times Rx over R15 plus Rx. So there's my potential at A. Then I will put something like, how do I want to do this? I'll put R63. That comes from moving the R to the other side. So I'll do R63 times R45 plus R63, all divided by R45 times R63. So again, I'm just finding the common denominator. And oh goody goody, you notice again the R63 cancels the R63. Oops, sorry. Somehow accidentally did that. And so at the end of the day, I'll rewrite this. We have VC is equal to V400 times the fraction Rx over R15 plus Rx. Notice that that's unitless. And we have a second unitless quantity, R45 plus R63 over R45. Ta-da! And of course, now that we have VC, we could always find the current flowing in the circuit, and that current I. Now let's take a look at this final answer for a second. First of all, we notice that our output potential is positive, right? And hopefully that should make some sense. We have put the input potential is running to the non-inverting input. And as expected, therefore, we end up with no such negative sign, right? It's positive. The second thing to note is, how do we control the amplification? One is, you notice the resistors prior to the input play a role. And then the second spot where we see our amplification are the resistors on the inverting input and the feedback loop. So there's two different places where we can actually control, if you will, the amplification. So what we have here is VC is equal to that 400. Excuse me, I said I was going to do numbers here. That 400, and then what do we have here? We have the RX, so the 60K, divided by the RX plus 15, so that's 75. Okay. Okay. And then we have the 63 kilo ohm resistor, and please forgive me, I dropped a decimal point. This is not 45K, but 4.5K. So be careful there. And it's a lot smaller. And this is all over 4.5K. Double check that. Right? 4.5. Okay, well, now we just run the numbers. And at the end of the day, I get something that says my output potential is 4.8 volts. So you can see that we're really close to the saturation limit. If I look back at the previous page, the op amp potential was plus or minus 5 volts. So we're pretty close already to that saturation limit. Okay. Now here's the advantage to having written this all out in variable form. Okay. Let's go ahead and use our expression that we had in order to find the ranges for Rx. Okay. Well, we know that the V out, so this is part 2 now, we know that V out, what I call VC, has to be within this range of potentials. And so I have -5 must be, I guess I'll put the strictly equal sign in there. -5, we have all of this other rigmarole, which we could probably keep. Then equal to 5. Well, we're going to have to move things around, do some algebra here to get Rx by itself. All right, best way forward is straight through. Okay, so here at this point, we're going to have to break it into 2 separate pieces, right? I need to consider this piece, and then I'll have to consider this piece. So right now I'm writing 2 equations as one, but now I've got to separate it out to actually find the true values. Well, so you can see, if I think of rigmarole, I've been calling it rigmarole, but let's go ahead. This whole thing that I'm underlining is just some constant. I'll call it a constant, and I'll just give it a fancy C here. Okay, that's just some constant. In fact, I'll call it negative constant because we have that negative sign there. So I'll call this a negative constant. So what do I have at the end of the day if I consider this left equation? I have this negative constant times R15 has to be less than or equal to Rx 1 plus this constant. Right? If I move this constant times Rx, I have to move it to this side of the equation. So I get a plus sign. Okay. And so what do I get at the end of the day? I get we'll leave it like this. We get negative constant times R15 divided by 1 plus that constant. That has to be less than or equal to Rx. And if we treat that right side of the equation, okay, what would we get? We would have something that said Rx must be equal to the constant times R15 over 1 minus whatever that constant is. You see right here, the only thing that's different is that lack of a negative sign. So there's the two equations that I have to solve in order to find my saturation things. Excuse me, this is not strictly equals, this is less than or equals to. Now we're off and rolling like a bale of turtles. We better figure out what that constant is. So what is this constant going to be equal to? Let's find out. 4.5 divided 67.5, it's probably like 16, something like that. Times 5 divided by 0.4. Let's get a fraction here. So I get a constant that is 5/6. So now we can say, okay, well, negative 5/6 times 15k divided by 1 plus 5/6, that will be equal to my Rx value. Okay. And yeah, cool. I get something that says Rx must be greater than negative 68.18. Well, how about the other side? We get something that says 5/6 times 15k over 1 minus 5/6. So Rx must be less than or equal to, you see it, denominator is 1/6, then we have a 5/6. So 5 times 15, so we get 75k. And I'll put the ohms in there now. Now, what does this mean? Let's look at this left equation. Does it make physical sense to have a negative resistance? No, it doesn't. That doesn't make any sense. So how do we correct for this? This means that we can make that resistance as low as possible and never saturate the op amp. And the smallest resistance that's possible is 0. So at the end of the day, for the given situation, the range of Rx that is permissible is 0 to 75 kiloohms. That is the saturation limit. Well, I think that's all that I have for the moment, but we'll get another video of additional op amp circuits. Yeah, so let's keep on keeping on. Thanks for your attention. I'll see you next time.